Hello everyone, welcome to my YouTube channel. So I'm going to solve the part 3 problems. So start with question number 12. So it is given that G be a group and H be a subgroup of index 2. Then commutator subgroup of G is always contained in H, and if any subgroup contains the commutator subgroup, then H must be normal. Okay, let's see. So basically, to solve this problem, you need to know the definition of commutator subgroups well, and to properties of commutator subgroup. If you know, then this problem is obvious. So let's solve. So commutator subgroup is basically collection of all element of the form x, y, x inverse, y inverse, such that xy belongs to G. Okay. Property. So one important property is number one, G mod commutator subgroup G is abelian. Number two, if H is normal in G and G mod H is abelian, then commutator subgroup is contained in H. So these two properties are very important. Now for option A, now for statement A, it is given that G mod H has order 2. That means it is abelian. Okay. Then clearly commutator subgroup is contained in H. So statement A is correct. And statement B says that H contains commutator subgroup, then H is normal or not. Okay. So to show H is normal, we need to show for all G in G and for all H in H, G inverse is in H. Now commutator subgroup is in H. That will imply G inverse H inverse is in H. That will imply G inverse belongs to H, which is H. That means G inverse belongs to H, and that holds for any G and H, because commutator subgroup is inside H. So all the elements of the form G inverse H inverse for any G any H in G inside commutator subgroup, and that is inside H. So that's why it is in H. Hence H is normal. So if you know the properties of commutator subgroup, then you can easily solve it. Okay. Now come to the problem number 13. Problem number 13 is a good problem and it's a difficult problem. Okay, so I'll solve it in a different video. I also left one problem here, that is I think problem number 8. So problem number 8 and problem number 13 both are two difficult problems, so I'll solve it in a different video. Let's solve problem number 14. So it says that theta belongs to open interval 0 pi by 2 and T is a linear map that sends every vector to its reflection with respect to the line 0 0 and cos theta sin theta. Okay, so you can solve it by geometric intuition. So say this one is R2, this one is unit circle. Okay, so this coordinates is cos theta sine theta. Okay, so this angle is theta. So the line passing through origin means this line. Okay, my picture is not good, so let's do it another picture. This one is theta, and this is cos theta sine theta. Okay, that is on the circle. So so the linear map is basically a reflection along this line, along this straight line. Okay, so the given options are basically matrix representation of T. So how can we get a matrix representation of T, of linear map? We are sending the basis vectors. So in the case of, since it is from R2, so we are sending 1 comma 0, and that will be our first column vector in the matrix representation, and 0 comma 1, that will be our second column vector in the matrix representation. Okay, so here 1 comma 0 is basically this, right? So if I do the reflection, that will goes to cos 2 theta comma sine 2 theta, right? Because you just reflect it along the line passing through origin and going through the cos theta comma sine theta. So that's why the first column vector will be cos theta comma sine theta. Now if you see the options, you can directly see that only option A have this cos theta sine theta in the first column. So option A will be correct. But you can also check that whether it's completely correct by using this. Now you have this one, right? This line. So if you reflect this line, then you will get this line, right? Again, this becomes a bad thing, I think, in a mistake. So some mistake is doing, that's why I have to do, sorry for that. So it is basically cos theta sine theta, this angle is theta. Now if you see this line, this angle will be pi by 2 minus theta. So this angle should be pi by 2 minus theta. Then this angle should be pi by 2 minus 2 theta. Then this will be cos pi by 2 minus 2 theta comma sine pi by 2 minus 2 theta. Okay. So this angle will be this. So the first vector will be cos pi by 2 minus 2 theta, and the second point will be sine pi by 2 minus 2 theta. So cos pi by 2 minus 2 theta is sine 2 theta, sine pi by 2 minus 2 theta is basically minus cos 2 theta. So clearly option A is correct. Okay. Now come to problem number 15. Problem number 14 is pretty easy. If you know this thing, then you can directly solve it by just visualizing. Okay. So for a problem number 15 says that for a polynomial f in two variables, real polynomials, we are considering the set collection of all elements or order pair a comma b such that f of a comma b is 1. And which of the following, I mean, for which polynomial the xf, the given set is compact. Okay. Okay. So by Hein-Borel theorem, in R2, any subset is compact if and only if it is closed and bounded. Now you can easily see that the given set for any polynomial, this xf is basically closed because of the given condition is a closed condition. Closed condition is means this set is obviously closed because whenever you are taking a sequence x and yn that converges to xy, that means what? Xn converges to x, yn converges to y, then xn square plus 4xn yn plus 3yn square obviously converges to x square plus 4xy plus 3y square since they are polynomial. And that's why if xn yn becomes it comes from xf, then basically xn square plus this 4xn dot yn plus 3yn square, this thing is always 1. That means it converges to this and that will be always 1 by by the definition. So it's basically given conditions are closed condition, so that's why the set are always closed. The problem is that whether the set is bounded or not. To check it is bounded or not, that you can directly check also. Okay, so let's first option A, it is given x square plus 4xy plus 3y square. Okay, so x square plus 4xy plus 3y square equal to 1. That means x square plus 4xy plus 3y square minus 1 is 0. Means x equal to minus 4y using Siddhar Acharya. Minus 4y 16y square minus 4 into 3y square minus 1 divided by 2. You get minus 4y plus minus 4y square plus 4 divided by 2. Now for all y in R, 4y square plus 4 greater or equal to 0. So you can always solution for x you can always have. So you can choose any real number y, then you can have a solution for this equation in terms of x also. So that's why you can choose any one. So range of y is unbounded. That means you are taking the collection. So range of y is unbounded. That means the set itself is unbounded. So this cannot be compact. But for the next one, for B, it's given x square minus 3xy plus 3y square. Okay. So it is given x square minus 3y square plus x square minus 3xy plus 3y square equal to 1. Minus 3xy plus 3y square minus 1 equal to 0. Means x is 3y plus minus 9y square minus 4 into 3y square minus 1 divided by 2. So 3y plus minus 4 minus 3y square divided by 2. Now 4 minus 3y square greater or equal to 0. That means y square less equal to 4 by 3. That means y belongs to minus 2 by root 3 comma 2 by root 3. This set. Right. Now you can see y maps to say 3y plus 4 minus 3y square by 2. This is a continuous map. Y maps to 3y minus 4 minus 3y square by 2. This is also a continuous map. And y takes the value minus 2 by root 3 to 2 by root 3, right? That is basically a compact set. So image of continuous function is compact. That means x takes value on a bounded set also, because here the range of this continuous function gives the values for x, right? So that equation satisfied. I mean that polynomials in two variables satisfies. So range of x is also bounded. That means the entire set becomes bounded. And you can also check similarly the option 3 will not work by same argument, that this also will be unbounded. You can have the range of y becomes unbounded if you solve in the similar way. That's why option B is correct. Okay, let now come to problem number 16. So the problem number 16 says that what is the number of distinct subfields of C isomorphic to Q adjoint cube root of 2. Okay, so this basically a plus b such that a comma b belongs to Q. Now observe field isomorphism, right? We have to find out the number of isomorphic subfield of C. So field isomorphism means 1 always maps to 1. So to check, say, any field isomorphism from Q adjoint cube root of 2 to say any subfield F of C, we need to check where this cube root of 2 maps to. So let cube root of 2 goes to alpha. So say this map is F. Then F of cube root of 2 is say alpha. And F is a field isomorphism, right? So F of 3 must goes to 3 because F of 1 is 1. That means F of 2 is 2. Okay, so F of 2 is 2. 3 is alpha cube. That means alpha cube is 2. That means alpha cube minus 2 is 0 in C. That means alpha is solution of x cube minus 2 equal to 0 in C, this polynomial. That means alpha is 2 power 1 by 3, 2 power 1 by 3 omega. Then choice of alpha is exactly 3. And the field homomorphism is field isomorphism is completely determined by where I am sending 2 power 1 by 3. So I can send 2 power 1 by 3 to 2 power 1 by 3 or 2 power 1 by 3 omega or 2 power 1 by 3 omega square. So that's why exactly 3 field isomorphism exist, and that's why only 3 subfield are there that are isomorphic to this. Okay, it is also a easy one. Now come to problem number 17. A similar type of problem I think comes in an exam. I don't recall, but which exam? Maybe TIFR, but similar type of question comes. So F3 denote the finite field of 3 elements. What is the number of one-dimensional vector subspace of the vector space F3 power 5? That means 5-dimensional subspace, 5-dimensional vector space over F3. Okay. So first you have to observe that what is the type of elements, right? F3. This the elements that looks like this. Then cardinality of this is basically 3 power 5. Now choose any x not equal to 0, any vector x, wx span of that vector. That is basically one dimensional, right? And any one dimensional subspace is basically generated by spanned by a single vector. Now you can observe that wx is same as w2x. Means span of x and span of 2x is basically same. So what are the number of, that means what is the number of distinct one-dimensional subspace? You have total number of non-zero vectors is basically 3 power 5 minus 1. And for x and for 2x you have same one-dimensional subspace. So you need to divide it by 2. Then you will get 1 to 1. That will be the correct answer. That is the distinct number of one-dimensional subspace. So any non-zero element span a one-dimensional subspace. But you can see that span of x and span of 2x both are same. That's why you have to divide it by 2. So 1 to 1 is the correct answer. Okay. So that's the third part of this video. I think in MCQ section only 3 questions are left, and before that or 2 questions are left, so I will make a separate video that. Thank you.